All right, we're finally ready to define our notion of sortedness. So I've just recapitulated the sorting functions here, right, written them up again, um, just so that we're all proving something about the same thing, right? Maybe you had a bug in yours or something, and now we'll all just have the same stuff. So let's define what it means to be sorted as an inductive proposition. So uh, here's three cases. So a list is sorted when it's the empty list. A list is sorted when it holds just one element, right? Can't be out of order. And a list is sorted when it's of the form x cons y cons l, x is less than or equal to y, and the list y cons l is also sorted. I want to note here that we're only talking about list nats because that's the only type we've really defined a proper notion of order for. You could define this in a more generic way if you said, well, give me some notion of ordering and I'll respect it, blah, blah, blah. But it's just going to be easier for us to do it just on nats. It's not hard in particular, it's just some engineering to get this relation to work on more generic types. Okay, so this is a notion of sortedness. You're going to want to check it in your head against is sorted. Think about that for a bit. And one way to check that is to double check a positive example. Does it really let us show that the list 1, 2, 3, 4 is sorted? So let's see. So how might you prove this? So we have a list 1, 2, 3, 4. We can't use sorted nil. We can't use sorted 1, so it's got to be sorted cons. Okay, we have to show that 1 is less than or equal to 2. Okay, apply LES. Apply LEN. All right, that's maybe old hat at this point. Okay, now we have to see that sorted 2, 3, 4. Okay, apply sorted cons again. So you'll notice here I'm actually not using bullets for these subcases because I'm marking off the sort of like side branch. And I think this ends up being a nice way to look at it. Okay, same story. So actually, in fact, this same proof script will work again. Apply sorted cons. Got the LE proof. Now we have to show the list 4 is sorted. Now, sorted cons won't work. Sorted cons only applies to lists with 2 things in it, right? If we try to do that, we'll get yelled at. Right? It says, I don't know how to unify this thing with 2 conses onto a tail with that. But there's a separate thing, sorted 1. Ah, perfect. Now, you might look at this definition and say, that's not how I think of sorted. Sortedness is about this. Okay, for any pair of indices that are sort of valid for the list, if I look up the nth element from the list, then it'll be less than the other nth element. So here we're using defaulting here to say 0 or whatever as the default if you go out of bounds. And that's true. This is another definition of sortedness, and it's a good one. And if you first started programming with arrays, maybe as is not uncommon, then this may be the first way that you think about defining sortedness. One tiny note: this notation I less than j less than length al is really just a sort of a macro for I less than j and j less than l. Sort of a nice syntactic convenience. Mathematicians write inequalities and inequalities in chains like this all the time, and we can support that too. So this sorted prime is another perfectly reasonable definition. You might wonder, why would you want one over the other? We'll see in the end that sorted is so much easier to work with than sorted prime. Sorted prime is a disaster for doing proofs. So there's some optional exercises at the end where we'll have you try to do it that way, and we'll relate sorted and sorted prime. And you can definitely get it that way, but it's just a much harder way to go. We'll revisit this in a bit. For now, we're going to say something is a sorting algorithm, right? F, a function from listNat to listNat, is a sorting algorithm when for any list, its output is a permutation of the input list, and its output is sorted. Absorb that for a moment. What goes wrong if we leave this out? Pause the video if you need to. Well, if you didn't have this permutation requirement, I could define a function f that always just returned the list 0, or the list 1, 2, 3, 4, or the empty list. And it would certainly always produce a sorted output, but it just wouldn't have anything to do with the original list, right? You really want it to be your elements, the things you started with, but sorted. Okay, in the next video, we'll spend some time thinking about sortedness, and that should be fun. And then after that, we'll finally actually prove that sort is a sorting algorithm. Okay, we're getting there, folks.